I've chosen mechanical engineering for studying because my dad, he was also a mechanical engineer, and when I grew up, he played a lot of mechanical stuff with us kids. So starting with Lego and all that stuff, and later on we built all kinds of stuff, and so I would say I really grew into it, and then when I decided to go to university, so I think it was the topic where I was interested in most. I think the joining, what we require in future, has also to do with Industry 4.0, to get rid of very stationary tooling, that we have a more flexible way, and not only, you know, there's so much research going on with just software, but I think this flexibility is also required in joining techniques. I think the next great breakthrough about aluminum and friction stir welding, I think, is this one over here. So we invented new joining techniques to join aluminum and steel. Today's car bodies are mainly from steel, and I think it won't change all of a sudden completely to aluminum. And what we offer here with this possibility is to make this change more gradually. Friction stir welding is a solid state process, so we are not melting the materials, and this makes it possible to join also materials that are very different in strength. So we are able to join here aluminum and steel, and the joint quality is that high that it's possible to do the forming operation after the welding. So I think before friction stir welding, there have been a lot of tests and trials to join different materials like steel and aluminum, and to be honest, they had a little bit success, but I think it was always too small for industrial application. Perhaps there are some very few test cars that are driving around that are joined by laser or something like this, but with friction stir welding you really have a process that's stable, that's reliable, and which I think is ready for mass production. Since FSW offers a great strength of the joints, much greater than, for example, from laser welding. So in our experiments, we have like 50% more strength. You can save 30% material or weight. So I think you can use it in a lot of different applications. I think with electromobility, the car body has to become lighter, and I think this could be one application. And I think also for the battery packaging, which has to be absolutely closed and safe. So I think this is a good application for friction stir welding. Faster machines, also cheaper machines, more flexibility, better control options. I think right now many people work on different details, and I think if it comes all together, this might be a really big breakthrough. We have to look that we integrate friction stir welding in the whole process chain to get the best out of our aluminum, the best strength, so we are able to do lightweight design. And I think post-weld heat treatment, or the knowledge when do I weld the material in which temper state, I think is a key component onto that. So I think it's very important to look for the whole process chain and to combine friction stir welding with different and new tempering methods. For simulating friction stir welding, we use the commercial software AluQuébec, and we extended it by our own material models and subroutines. I think there's a lot of good publications out there about friction stir welding. I, of course, can recommend the papers from our working group, Aluminum and Steel. I think these are strength values that we generated there, which you cannot find somewhere else in literature. And I think we will also publish a lot of in this topic in the next couple of months or years.